so I'm sorry for the delay. Had some technical problems with starting the recording. So what we did last time, after having looked at propositional logic and sub-solving, we started with first order logic and first order theories. We have seen that what is first order logic, which components it has, and besides syntax, we also looked at the semantics. That means the meaning of first order logic formulas. And we have seen that what is the meaning of that the structure satisfies the theory. We have also seen what is validity and satisfiability, and especially arrived by the theory. That means if I have first order logic with a signature, then I can restrict the set of structures which can satisfy it by defining a set of axioms. And satisfiability means that the axioms must also satisfy by the structures and not only the formula. This way, for example, I can restrict the meaning of how to interpret equality, or another model which we looked at, another theory which we looked at how to interpret besides equality also addition. Okay, this was where we stopped last time, and what comes next is we can restrict the set of satisfying structures by theory, by axioms defining a theory, but we can also restrict the syntax of formulas. And this makes sense in restricting the expressivity, and you can do similar things like with the axioms. And if we do this, so if we restrict the grammar, then we talk about logic fragments. For example, we can say we have a signature, we have numbers with equality and addition, so basically the Pressburg arithmetic, but we do not allow quantifiers, universal and existential quantifiers. And then we have the quantifier-free fragment of a logic. Or we can also say we would like to have constraints of Pressburg arithmetic, but we would also like to allow conjunctions. For example, to apply the simplex algorithm, simplex cannot handle arbitrary Boolean combinations of constraints, but only a set of constraints. So if we restrict this to a fragment, the conjunctive fragment, and restrict the Boolean operators that I can use, and then we can develop special algorithms for those logics. So let's assume that we have now first order logic. The signature is empty, or as we have seen last time, we need basically one predicate that lists Boolean variables to formulas, Boolean formulas. So assume that it is silently done. If I have a Boolean variable, if you remember, this is a variable, and this is not a formula. A formula is made from this variable by applying predicate to it. Yeah, is it clear what I'm talking about? Whom it is not clear? Okay. So assume our signature is empty. So what is the quantifier-free fragment of this theory? This you already know. So I do not have any functions or...
I think in mathematical logic we said that equal is always defined.
This is a matter of definition. So if you say equality is in your logic, this is fine. But for example here, exactly in this we would not like to have it.
Okay, I was wondering because you were using...
Yes. Sometimes we put in equality because it is so widely used.
Yeah, okay.
And even here we could have it, it would not
make much of a difference, but I was just wondering.
Yeah, so you can define equality to be already in the signature, but you do not install it. So if I have now no axioms, and I have just a sigma, an empty signature, which logic is it? And I take the quantifier-free fragment, so I do not have exist and for all in the Boolean combination. Which logic is it? What can you write down still? Assume also last time we said that variables we do not list in the signature. You may have variables. No? Exactly. It is propositional logic. The only thing what you can do is you have the Boolean variables and you might have the Boolean composition because it is in each first order logic. Yeah, the Boolean skeleton is given and what you can change is only the theory behind. It means you can use different domains and define different functions on these domains and different predicates that lift terms from this domain to the Boolean. Like, for example, equality or less than, or such operators compare two terms in their theory, and then it is then true or false, so you lift up from the theory to the Boolean. And in propositional logic, the only thing what we need is Boolean variables, and the rest is given. We have the Boolean structure already defined in the first order logic, and if you do not allow quantifiers, it is propositional logic. Like, for example, such formulas, this implication and disjunction is already in the first order syntax. The skeleton is given. But these things are very simple because the signature is empty. So, and if we do not restrict to the fragment, quantifier free, which logic do we get then?
Sorry, I wasn't there the last few lectures, so I'm sorry. So variables can have Boolean as well as values from the universe, or is there the
variables are typed. So you have
set of variables from the universe instead of Boolean variables.
Boolean variables are special variables with the domain Boolean. And you can have variables with the domain integer.
Can be multiple universes, basically?
Yes.
Okay, thank you. Sorry.
Yeah. And each variable, the only restriction on the values is that they must be typed correct. But we assume that the names are already typed, so you always know which variable has which type. So if I also allow quantifiers, which logic use then? First order logic. So yeah, it is called quantified Boolean formula, but it is propositional logic with quantifiers. It is also called QBF. We will not look at QBF decision procedures, but there are also similarly to such extensions to it. They use similar methods to solve also quantified Boolean formulas. Okay. There are of course different logics, and what we will look now in the next is first equality. So if you have equality, you already said most times it is already included in the basic definition of first order logic syntax, so you do not need to put it into the signature. If you have equalities, then as we will see, if your domains are unrestricted, then you can check equalities formulas involving equalities, so you can lead it back to propositional logic. Then we will look at uninterpreted functions, and afterwards we will come to the numbers. So we will have integers and reals, and the operations first you can have only addition and of course comparison between terms, or you can have addition and multiplication. This is the same for integers as also for the reals. And if you have integers with only addition, then we call it Presburger arithmetic. And if we have also multiplication, then it is the Peano arithmetic, or also called these are called arithmetic. For the reals, it is called algebra. Arithmetic and algebra are two related words, and basically which one is used is more on the aim of where you use this theory. We use the historical name. That's why also if you have the reals and only additions, then it is called real algebra, which is linear. And if you have also multiplication, then it is called real algebra, which might also be nonlinear. So if we look also at these four, there are also further theories which we will not look at, like the theory of arrays or theory of pointers. If we will have some time, then we will have some not so deep insight into these areas. But first we will look at theories containing numbers. Okay. Now what we have looked at is how to define those theories using axioms. And as we will see, axioms are not always well suited to define these theories. Sometimes we will use grammar rules. This probably you also know. Here is an example for equality logic, which we will look at next. Instead of defining some axioms restricting the meaning of the equality, we just define the grammar. Instead of giving a fragment by saying that, for example, it is a quantifier-free fragment of this logic, we just give an abstract grammar telling that the formula is either an atom or a conjunction or negation of formulas, and we say what an atom is. This is a Boolean variable, or we have comparison, equality between variables and constants, or constants and constants. And we say that by equality we mean equality, normal equality, and not something else. So this is either I can define a fragment by saying that is a, for example, quantifier-free fragment of something, or I just redefine the grammar of first order logic that restricted to those parts which I would like to include. Okay. And so now we have a first order logic theory, perhaps a fragment of it, defined by some grammar restrictions, and we have formulas in this logic. Each formula can be seen as a language. Namely, the words of this language are those assignments which satisfy this formula. And then, as you know, languages have different expressive power. Sometimes you can compare, sometimes they are not comparable. This can be also seen similarly for logic. To illustrate this, let's say we take now a fragment of propositional logic, namely, first, we only allow formulas in conjunctive normal form, and secondly, we allow clauses to have exactly two literals. This is called the 2CNF. If we make this restriction, syntactical restriction by an abstract grammar, then it looks like following. A literal is either a Boolean variable or its negation, and the formula is either a two literal clause or the conjunction of two literal clauses. Here you can see an example of a 2CNF. And now we define a fragment, and this fragment can be perhaps only a syntactical restriction, perhaps it is a real restriction restricting the expressiveness of the logic. So the question is, did we restrict the expressiveness by restricting the syntax? Put it another way, can we express whole propositional logic in 2CNF? What do you think?
Cannot, because you can solve 2CNF in a number of times, if I remember correctly.
Okay, then you should give the proof that this is possible.
I think they're Horn clauses, so they're implications or constants, and then we can take all the constants as a single positive or a single negative literal. Oh no, we didn't allow single literals, right?
What do you mean with single literals?
Just implications, basically, a whole set of implications, right?
Okay, you can see them as implications.
And we can clearly assign our left-hand side. Actually it's not that simple, but I think you can really grab from it. I have to think about it.
Okay, there is an easier proof. And, but still you may have it is not an explanation why you don't have exponential solution. solution is the following. You know that if you have this closed with 3 slippers, then it has 7 solutions. Yeah, because the only solution which we exclude is if all 3 litters are full. Yeah, this is clear. Okay, if we would like to express it in 2 CNF, yeah, with the empty formula without closes, you have 8 solutions. So it doesn't fit. You must at least one close with 2 litters. What happens if we add one close with 2 litters? It removes 2 assignments. Namely, not both litters are false. If, for example, this close is x1 or x2, it excludes the combination where both x1 and x2 are false, and x3 doesn't matter. So you remove 2 possible assignments. First, where all are false, and one where x3 is true and the other ones are false. And you already removed 2, but you wanted to remove only a single one. So there are only 6 solutions, and if you add new clauses, it will only remove further solutions. So this is a very simple proof that 2 CNF is not so expressive than proposition logic. So we can compare these languages like inclusion. If they are comparable, then one of them includes the other, or they include each other, then they are very powerful. So 2 CNF is, for example, less expressive than proposition logic, so that we use this symbol. But there is only a partial order. So it is not always the case that one logic includes the other. And you might have quite disjunctive, or this case where sorry, they partly can express the same, but both languages have some parts which are not expressible in the others. So they are not all comparable. What we are interested in is now theories have different expressive powers, and we will look at different theories in this lecture, in the remaining part. So the question is, do we look at some fragments? Why do we look at some fragments instead of looking at the whole? If we look at the whole, then we are more powerful, and we can solve more problems. So what can be a reason of restricting to fragments?
It becomes difficult to solve it or even impossible.
Exactly. So it can be difficult or even impossible. So an example is the following. If we have here that axiom system for propositional logic, it just has 3 rules. And it is the whole propositional logic, though it is already a fragment, quantify a free fragment, but this is sound and complete. That means if something is true, I can use these 3 rules to derive all true assignments, all true formulas, and I can derive exactly those which are true. This is just that if the consequence is true, then the implication holds. And if A implies B implies C, then also if A implies B, then A implies C, and also the negated implication holds. So these 3 are sufficient, so we do not have any necessity of further restricting to smaller fragments. But if you look at more complex logic, first to the theories, you can have axioms which are not sufficient for proving all t-valid formulas. And if you look at the example of first order piano arithmetic, where you have integers, addition, multiplication, and equality or comparison doesn't matter. If you have here equality or less than. Then we have an axiomatization which says that each number has a unique successor. Then we have a rule for induction, and we have each 2 rules for addition and multiplication. For addition, we state that 0 is a neutral element, and that addition can be computed recursively. And the same for multiplication, that x times 0 is 0, and that also for multiplication multiplication, computing the for successors, you can reduce to the predecessors. And this logic is undecidable. So what to do? If it is undecidable, we remove some syntax and restrict it to a fragment. And this fragment is, if we remove the multiplication, then we end up by Pressburg arithmetic, and this is decidable. This is a very typical example by removing, restricting some parts, in this case removing even something from the signature, leads from undecidability to decidability. We will come back to it a bit later. What is important now for us in the moment, so from this whole talk about first order series, is that we have quite a scale of different first order series, depending on how we define signature and which fragments we take. And what is interesting for us is, first of all, of course, first order series which are useful in practice. That means in which I can express practically relevant problems. So they must be expressive enough to express certain problems. The language, the smaller the language or the less expressive it is, the easier to decide. So there are already theories which are solvable in polynomial time, but they are in general, there are exceptions, but in general not so interesting because they are not so powerful. Then we have something in between, which is already exponential, but they are still decidable, and this is what we talk most about in this course. And then there is this undecidable fragment, which we will deal a bit, but we mostly concentrate on this big part in between. So, to conclude, we look at theories which are expressible enough to state something interesting. They should be decidable, or at least semi-decidable. And we would like to restrict us then to fragments where at least these fragments we have the chance to solve efficiently. And of course, if there is a language which we can gain some more expressiveness without losing efficiency, then we would like to maximize expressiveness and also minimize the computational complexity. So before we go on to decidability and undecidability, to the relation of languages. Assume we have two theories. You can also look at them as languages. These are the formulas which are satisfiable. And the satisfiable problem is decidable, and it is in the same complexity class. Does it hold then that the satisfiability problem of the first language or the first formula is reducible to the satisfiability problem of the second one? Is it always true? They are in the same complexity class. You can think of now here a formula, but you can also even think about the whole series in general. These are arbitrary formulas, no special formulas. So both problems?
What exactly does complexity class in this context mean? Does it mean like
Polynomial?
Polynomial?
Exactly. Two problems are in the same complexity class. That it always implies that I can reduce one problem to the other.
Reduce means polynomial size reduction, or?
Yeah. Reduction in this complexity.
Can I just say I solve the formula in one, but because I have complexity, however,
in the same complexity class only means that L1 and L2 both have a solution in this complexity. But now the question is, can I solve L1 by solving L2?
Actually, couldn't L1 be solvable in P and L2 only in NP? Then both are in NP. So assume that the decidability for L1 is polynomial and for L2 are exponential. Then both are in the same complexity class NP.
Yeah, no, I mean the first.
So, and especially there for both L1 and L2, there are no smaller complexity class.
Then all complexity class, the set of complexity classes they are included in is equivalent.
Okay. Then still we want to try to overcome possibly different signatures.
Yeah, the signatures can be different, so they might stem from different logics.
But still the question, I think, is what reduce means.
Reduce means that you define a transformation such that if you solve the second problem, then you get the solution of the first problem.
The question is, what kind of complexity am I allowed to use in this? I mean, I could use
the same complexity.
So I could use L1, the problem from L1, and the solution is the solution of true. Then my the solution, so my formula in L2 would be true. If it is false, then the formula would be false. Then I just need to solve the formula true or false, which is trivial, and then I have the solution for my original formula.
So really, is it a polynomial reduction or a reduction of the according complexity?
The reduction should be in the complexity classes in this area. So let's say they are polynomial type solvable, yeah, in the class. And then L1 can be reduced in polynomial time to a problem L2, such that if you solve L2, then you solve L1.
Yeah, then I can take formula phi 1, which is valid in L2, and the formula phi phi 2 is L2, and formula phi 2, which is not defined in L2. And then I solve the input formula on L1, which is obviously possible in the complexity class. And then if it's true, the reduction goes phi 1, and if it's not, that's phi 2. It returns phi 2.
Actually, I don't think there's no way to satisfy the formula.
So again, I have a problem L1, and let's say the complexity class is
So let's say you have some
just
NP complete problems.
okay, so I have a certain complexity and there is a transformation of this problem to another one in this complexity such that I can solve it in this complexity, let's say solution or answer, and then I get the solution of the first problem a kind of immediately, but let's say even in this complexity class. Perhaps also I have to transform back the answer.
Is the solution, is it satisfiable or is it an assignment to the variable?
Actually, it doesn't matter. But let's say these are sentences, so it is yes, no answer.
So I can just solve the formula from L1 and just generate a formula in L2 that's true or false. I mean, yeah.
Yeah, okay.
So therefore the question whether reducible means polynomial time reducible or not. I mean, you can always reduce it when you have the power to continue.
No, it is a kind of active satisfiable. So you generate an active satisfiable problem, L2, such that if you solve that, then you have the solution for L1.
Yes, but you do have. I mean,
but okay, this is one point. This could be also the proof, a simple proof that it is always possible. Of course, if they are in the same complexity class, in your studies probably you did a lot of such reductions already. Instead of solving one problem, solving another, and leaving back the result. But what is more important is for undecidability. If you want to prove that something is undecidable, then you take something like the halting problem on two counter machines, you lead it back, and then you have a problem, and you show that if you that this, if this is decidable, then the two-counter machine program should also be decidable. Yeah, you reduce the problem to that. And then you can show that, therefore, if you can solve the class of problems, or the other way around, you can solve, if you can solve the two-counter machine problems, then it is sufficient to solve your problem. Then what is needed to solve your problem, then your problem is also undecidable. So for undecidability, such reductions are used very often, frequently, but also for the complexity. You do not, it is not easy to show that a problem belongs to a complexity class by constructive proof. But what is much easier, if for one problem it is shown, then you can reduce that problem to your problem, and then you show thereby that you need at least the same complexity. And if you do the other way around, then you know that it's there. So a last question for first order logic. Now we turn it around. We have two theories, and we know that we can reduce L1 to L2, and we can reduce L2 to L1. Does it mean that they are in the same complexity class? Is it always the case that these two problems are reducible to each other, then they are in the same complexity class?
No, I don't think so.
Because,
For example, every instance of the Grenzprogramm with arithmetic, or for instance of the piano arithmetic, we said before that the last one is undecidable.
yeah, but piano we cannot reduce to Grenzprogramm, but there is another reason.
No, but we can reduce Grenzprogramm to piano.
Yeah, but it is each other.
If the reduction once again has the same complexity than the decidability problem, then they have to be the same complexity.
Exactly. So it depends on the complexity of the reduction. If it is in the same class, then yes. If not, then perhaps. So, and now I thought before we go to the different decision procedures, we take today a bit more time to deal with decidability. Not so much because it belongs to the decision procedures. The decision procedures mainly give algorithms for checking satisfiability, but because it is theoretically interesting. And what I would like to talk about today is not so much theoretical insight than giving you a historical overview of what happened in the last about 100 years. Oh, I'm sorry, I didn't change the, or didn't check in the file. So, decidability. We have already seen some first-order logic. For example, propositional logic. Is this logic decidable? My answer is very easy. Is it decidable? Yes, because how do we prove?
Try and error.
Okay, try and error. We could prove all assignments, and since we have only finitely many variables, we have also finitely many assignments, but a constructive proof could be also that we gave an algorithm, a subsolving algorithm for solving it, and we have proven that this algorithm is complete. That means that it terminates always, and it is also correct. That means it always gives the right answer. And we have I already told that next one we will look at applicational logic. We will lead it back to subsolving. The same for uninterpreted functions, we will reduce it to subsolving. Now probably you know simplex, what can solve linear real algebraic formulas. Real algebra, in the nonlinear case, if you have the reals with addition and multiplication, we will look most of all for the virtual substitution because it is very nice algorithmic.
That real algebra then includes the equal sign or the equal relation?
Yes, actually stronger if it is an order. And since you have also negations, you can also have equal orders. So you can compare terms. And if you have a natural number, then we said if we have only addition, then it is decidable. We also look at two algorithms. But if we take the natural numbers with addition and multiplication, it becomes undecidable. So the question is, what does it mean now, undecidable, and how?
The question is the arithmetic with set instead of n and plus and multiplication decidable?
Actually, it doesn't matter, but it is the natural number. Basically, if you talk about transpose arithmetic, then you
No,
need the natural number.
it's the piano arithmetic if I replace n with that. Is this one decidable?
No. You get the multiplication inside.
No. I want to compare real algebra with piano.
N and Z is the same. It doesn't matter.
It doesn't matter.
But I can express in real algebra that number is a natural.
No.
We have 1 and 0.
But you cannot list all natural numbers. You don't have the axiomatization. This is exactly the point. That for the real, you have no formula to state that in an interval there is an integer. And you cannot distinguish. This is the hard part. So you would think, basically, intuitive, okay, in piano arithmetic I have less. I have only the integers. Now I come to real algebra, I allow more. I have also the rationals and the irrational numbers. So what I can decide in the real, why I cannot decide the restricted part. But this is exactly the point, to check if in an interval there is an integer. This is not trivial if the bounds are given by variables. If it is decidable. Not trivial means it is not decidable in general. So, what does it mean and how do we know it? How we came to these results? Actually, of course, mathematics is very old. So, go back to Greek mathematics, perhaps they started, you cannot say their first number, but basically to Greek mathematics, we can follow piano arithmetic, so addition and multiplication of the natural numbers. This is something very natural because, of course, there were things to measure, there was money to exchange, or if you exchange things, you would like to know that it is fair. And from there on, mathematics developed from this very practical application, where you have rather informal statements. It developed by the time to something formal. And it is not quite clear without explicitly discussing it that these developments are relatively new. Most of the results to undecidability or decidability stem from the 20th century, and basics for them were built in the 19th century. So let's say we talk about the last 200 years. Okay, we look at four names before we come to undecidability. Grafman, it is about geometry, and in geometry, firstly, it is intuitive. What is intuitive are two-dimensional and three-dimensional spaces. And geometry, start of geometry was exactly in those spaces. And Grafman was the first one who said, if we look at geometry as algebra, then 2 or 3 that do not have any special meaning. You can have any possible dimension, and it is in fact even unbounded. So we generalize 2 or 3-dimensional geometry to linear algebra and vector spaces. And if you have the word algebra, it was not called algebra at that time, but this gives the name of counting. Yeah, that means that geometry can be led back to something which has to do with counting. Then, from the natural numbers, 3 part went to extending the natural numbers. That means if we take the rational and irrational numbers, then we have something without gaps. Especially an irrational number divide rationals into two sets. So if this is the line of the real numbers, then you have an irrational number, then you know that the rational numbers are either one set is smaller, one set is larger, but all are comparable. And the real numbers are without holes. That means every point on the real line is an irrational number. A real number. Okay, so now we have the two domains from the natural numbers and from the real numbers. And then one point to the infinity, Dedekind was the one who formalized infinity. This is also a very important point. Firstly, he defined something like similarity of sets or of domains. He said that if you look at this definition, a set is infinite when it is similar to a proper part of itself. And similar means that you have a one-to-one correspondence between two sets, a kind of bijection. So, for example, you have the natural numbers. If you take the whole natural numbers, or if you take only the square numbers, then you can define a function which assigns to each natural number a square number and vice versa. And what Dedekind did additionally, what was very important, is that he said, okay, natural numbers is one example for infinite sets, and to define what is a natural number, this can be done using axiomatization. That means you define first of a theory, and by axioms, you restrict the interpretation of the variables to the interpretation of the natural numbers. And he made this axiomatization. These axioms do not carry his name, because 1 year later Peano formalized a more simple axiomatization, and that's why we call it Peano arithmetic and not Dedekind arithmetic. Then Frege came, and what he did is, before him there were already some formalizations of what is a number, what is a natural number. And we have seen that geometry was interpreted as arithmetic. So there were already formal basics for handling them, but still the Boolean combination of constraints was not formalized, and most of was a nesting knot. So if you have a non-nested formula, it is much easier to interpret that than a nested one. Iteration, recursion was not defined. So he made the last part, namely define functions and variables, and define formally the Boolean Boolean operators and also the quantifiers sum and all, that means they exist and for all. So at least now they had a formal logic. Mathematics had a formal logic, and in this formal logic, Frege's goal was, until this point, there was proof. But in this proof, there were always a portion of intuition. That means you say, okay, I put an argumentation in natural language, and I try to convince people that it is this way. But convincing people by natural language, we have seen that it is not without possible mistakes, making mistakes in proof. So Frege wanted that the mathematical proof should be formal. There should be no room for intuition. What should be is axiomatization of the domain, axiomatization of the operations and functions and what we have seen in first order logic. And on this basis we can make formal proofs. These are unmisunderstandable, they are precise, and everyone can just check them. And it is not a matter of whether I believe or not. So at this point, we were at the point where the logic is there, it is everything formal. Even the axiomatizations of the different logics are there. But still, we have one last question which came and solved by Gödel and Turing, and this is soundness, completeness, and consistency, which we already had looked at the very beginning. So if you have a logic, Peano formalized the axiomatization of Peano arithmetic, and now the question came, if you have Peano arithmetic, this means the natural numbers and addition and multiplication. This is the mostly used logic at this time. Then you can look at the axioms. They are quite similar as what we have looked at. This is the axiomatization of the natural numbers. That means 0 is a natural number. Every number has a successor which is unique. Then for the addition, we say that the successors of two numbers, this is still the uniqueness of the successor. The successor equal than the number also. Then for addition we have 2, the same as before. For multiplication we have 2 as the same as before. And what was first just referred to as induction rule is written here. Is that what you know under the induction? That means you show, given a formula with k plus 1 variables, you show that this formula holds for 0 if the first parameter is 0. And if the first parameter is n, then you show that it holds also for n plus 1. Then it holds for all natural numbers. This is a certain proof, inductive proof, which you probably learned either at high school or in the first semester. Now what is the problem with this axiomatization is that you have here for each k in n. And you also universal quantification. That means that you have basically infinitely many instances of this rule if you instantiate it for each possible natural number. So it is an infinite axiomatization. And that's why, for example, if you want to prove that 5 is a natural number, this is still fine, because we use axiom 1 to prove that 0 is a natural number, and we use 5 times the second axiom, A2, and then we have shown that 5 is a natural number, which is 5 is a shortening for 0, so the fifth successor of 0. But if you want to prove that for each natural number it holds that the number is not equal its successor, this is much more complicated, because you would need for each n, you need this induction axiom, but to show it for each number, basically you would need infinitely many application of it. But doesn't matter. Even if you have an infinite axiomatization, it does not mean that your logic is undecidable. After Peano fixed his axiom, Russell and others agreed that these axioms indeed define that what was meant by the natural numbers with addition and multiplication. So the general opinion was this axiomatization of Peano arithmetic is correct. But some others, for example Henry Poincaré, was more cautious, because he said, okay, they think that it is this way. Intuitively, I would also say that it is correct, but are we sure that there are no mistakes in this axiom? But we say today, are they consistent? That means, can it be the case that using these axioms, we can derive some contradiction? That means, for something we can prove that it is true, and we can also prove that it is wrong. And of course, the general opinion was that it is not possible. But it was about to prove it. And here that in a congress in 1900 suggested to solve, or he collected 23 problems which were not solved in the last century and which should be solved in the next one. And one of these problems was to prove that the Peano arithmetic is consistent and complete. And a lot of people started to work on this problem. And the first one, so here that aim was, and he was convinced that it is true, to show that in this Peano arithmetic is, the whole mathematics, if it is based on this theory, then it should be proven to be consistent and complete, such that we know that all mathematical truths which we deduce using these axioms are indeed correct, because otherwise we cannot be sure. If we are not sure that it is consistent, our logic, then we cannot be sure that anything we derive makes sense. So his Entscheidungsproblem was that shows that there is an effective procedure such that this procedure can solve in finite time, can give you the answer whether a given mathematical proposition in Peano arithmetic is true or false, or equivalently put, if a problem can be derived from a set of axioms or not. And these three terms you already know from our previous lectures. So soundness is one basic thing. Soundness means if you can derive something that is true. This is relatively easy to show, much easier than to show consistency and completeness. Consistency means that you cannot derive true and false at the same time, and completeness means that you can always derive either true or false. You can always prove or disprove a statement. And decidability means that, and this is from the practical formulation, means that there is a procedure such that if you give a statement in mathematics, in Peano arithmetic for example, it can definitely establish within a finite time whether or not that statement follows from the given axiom, whether or not this statement is derived. And this consistency and completeness are closely related, but they are still different. And if there is a mathematical theory which is consistent and complete, and it is at least as expressive like Peano arithmetic, then this is what everybody was expected and what Hilbert was aiming with his problem, to show that everything is provable what is true, and everything what you derive is true, so the mathematical building is stable. And then there were some major steps during this direction. So the goal was to prove that Peano arithmetic is complete and consistent. The first one was Pressburger, who just omitted the multiplication and said, okay, if we do not use multiplication, then he proved that Pressburger arithmetic is complete. Complete means that you have a decision procedure which gives you an answer to a question. So then Holland also worked on this problem, and he showed that if we take the multiplication but do not take addition, then it is also complete. So now we have both fragments but still not together. Then Harvey showed completeness of real algebra. If we do not take the natural numbers but the real numbers, then we showed it is fine with addition and multiplication. Then the next step was that Peano arithmetic, so So we have both addition and multiplication, but we take out the induction rule, then it is also complete. So people try to go from all directions, remove the part that they could prove, but they could not prove it for Opana arithmetic. And then Gödel. It is the same. If it is the whole thing problem, if it is piano arithmetic, you come up at the same thing. These were Gödel and Turing, who basically gave the proof that if you have a logic which is at least as strong as piano arithmetic, then it is always incomplete. What did Gödel do? He said that, exactly. So if you have any consistent theory, this is of course the precondition, which is at least as strong as piano arithmetic, then it will be possible to construct an arithmetic proposition G such that neither G nor its negation is provable. That means it is incomplete. Okay, and the proof is he has shown that you can encode mathematical proofs in first order logic over the natural numbers, addition, multiplication. So in piano arithmetic, you can encode proof. This is basically already the sign that this logic is too expressive to be decidable. At each point, if the logic is as strong that it can argue about itself, then it is undecidable. So, and Gödel has shown that piano arithmetic is strong enough to encode proof in the logic itself, and this encoding is truth-preserving. That means you can indeed formulate something that P is derivable. There is a proof for P. And then he argues as follows. Assume that there is a proposition G which encodes that G itself is unprovable. And then now the following assumption. If the logic is complete, then since G itself is unprovable, if it is complete, nothing is unprovable, so G must be false. But if G is false, then the statement G is that G is unprovable, and if it is false, so you negate it, then you get that G is provable. And G, the other line is if G is false, then you know that not G is true, because we are complete. You also can prove that not G is provable. So now we derive that G is provable, and we derive that not G is provable. So our assumption that our system is sound is not given. Because we derive a statement and its negation. And thereby we have proven that our assumption that the system is complete is wrong. That means if you have a logic where you can encode provability of statements in the logic, that means at least as expressive as piano arithmetic, because there you can do it, then the system is always incomplete. This is put in this period. In a big extension, it does not say that the logic is always incomplete, but it says that that you can prove the only consistency of the language. Okay, the proof is actually the same like before. It's less back. I just go further. What remains still open is what they did in this proof is based on functions. So we say that a function is computable if there is an algorithm that can calculate its result in a finite number of steps. And what is not yet shown is that, so Gödel has shown that there are, if the theories are strong enough, they are undecidable, but they did not yet show that if the problems are basically classified in decidable and undecidable problems in a theory. There are some easier problems which perhaps you can solve, but there are perhaps maybe some more complicated which you cannot solve. And this could be that you still can distinguish between them. So given an undecidable logic, you could still have a function, you give a problem and it gives you back if you can solve this problem or not. And this was still open. And the last part, also to close this problem, was given by Turing, who looked not at from the functional side, like Gödel, but from the effectively computable side, that means from the algorithmic side. I assume that all of you know the voting problem and also the proof that it is undecidable. Is there anybody not knowing this proof? So I do not have to show that. This is basically also quite similar to Gödel's proof, but from the computable part. And he did not look for computable functions, but for effective methods, which is given a class of problems. For each of these problems, he will give an answer in finite time. It always gives the right answer, that means it is sound, and it works for all problem instances, that means it is complete. And he's shown that for programs, that termination is non-decidable, which is theoretically equivalent of, if we are talking about reducible, to the problem of decidability of Peano arithmetic. Okay, so if we have an effective method, then we can also say that this is an algorithm. And what Turing has shown is that there exist problems that cannot be effectively computed. That means in Peano arithmetic that there are undecidable problems in this class, that the logic itself is undecidable. So he formulated the voting problem and has shown that it is unsolvable, and by this he finished the last part of the proof. The Peano arithmetic is incomplete, and now we have a statement by Church. Church says this probably you also know. It says that if some algorithm exists to carry out a calculation, then the same calculation can be also carried out by a Turing machine. That means everything what you can compute, yes, you can compute by a Turing machine. This statement is not a mathematical form statement. That means you cannot prove it. It is kind of non-elementary, but it is basically accepted as a true statement. And this means also that Gödel and Turing part basically analogous and extend each other. So we know now that there are undecidable logics, that everything what is as strong as Peano arithmetic are incomplete and therefore also undecidable. And it was in 1977 where the first major example of an unprovable Peano arithmetic formula was formulated. So it is not so long time ago. That means incompleteness and decidability are, in contrast to other mathematical areas, are relatively new. So, do you have any questions? None? I think it doesn't, it is not good to start now with a new topic, so I will finish for now, and on Thursday we will look at equality.